Hi, Josh. Good. How are you?
Good. Well, scared. Like Thanksgiving break coming up. It's weird because all the exams are between now and when.
It's gonna get busy, that's for sure.
The end of the semester can be quite so rough.
Mhm. Hey, how's it going?
I live on the Daver side.
But
That's fine. Coming up at the end of this month already, so. All measures.
You have deadlines.
What?
Your deadlines.
Sorry, no.
You have deadlines. For what? There you go. And then you can stress on right now. No, they're doing that, they're doing this one.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon. How's everyone doing today? Doing good? Everyone got an extra hour of sleep yesterday? Hopefully. I woke up really early on Sunday morning. I forgot that it was daylight savings, of course, and then but yeah, it was I did not get a great sleep over the weekend. But I got good sleep last night. So okay, so we have quite a bit to do today. So first thing I wanted to do today was talk about the final project. So remember last time we were here last Wednesday, I mentioned that we would talk about it today, so I wanted to make sure we set aside some time to talk about that. Hopefully you guys are thinking about some groups that you guys want to form in, because the final project is a group project. Other thing that I want to do today is I want to finish up our notes on human motion kinematics. So there's a little bit more of the lecture that I want to go over, and then there's also one example that I want to do as well. Okay. The example that I have is, well, because I don't have that many great examples of this. It's actually the exam problem from last year. So if you want to get kind of an idea of what to expect from this section on the next midterm exam, that is it. Okay. All right, so I think that's about it for my announcement. So homework 4 was due last week. I'm still working on homework 5 for you guys. The plan is for homework 5 to be posted, maybe not today, but maybe tomorrow, and then for it to be due on the Monday before we go on break. Okay. Yeah, question.
Just to confirm, midterm 2 is gonna be on the 20th, right? If I'm correct?
Yes. Yeah. So that's the Wednesday. So our schedule is a little bit weird because we actually technically have class on the Monday of Thanksgiving week. I have to be here just because I'm contractually obligated to be here, but I'll be streaming on Zoom. So if I'm teaching in an empty room, I won't be insulted just because I don't really want to be here either. But I have to be here. So our midterms will be the Wednesday before that. So I believe is the 20th. Yeah. Oh, other announcement. I'm forgetting something. So I just remembered today that this next upcoming Monday is a holiday, which is the reason why we're teaching. We're having work on Monday of Thanksgiving week. So Monday is Veterans Day, so there won't be any class that day. So I won't be here. So this week we'll have 2 lectures. Next week we'll just have the 1 lecture on Wednesday. Okay. All right. Any questions before we start talking about the midterm project? Okay, or not the midterm, the final project. I'm sorry, my mind is on another classroom. Okay, so let me go ahead and share my screen. Okay, can everyone on Zoom see my screen?
Yeah.
I'm going to assume that's yes. Okay. Okay, good. Okay, so this is the final project for this class. So the instructions for this are posted on Canvas right now. So actually, I posted it last week, so some of you may have already had a chance to look at it. But basically, the general idea with the final project in this class is for you guys to get a chance to research something of interest to you that has to do with biomechanics of motion in some kind. Okay. Now, we've been mostly focusing on human motion, so human, body parts, human, things like that. But, for this final project, you can branch out a little bit as well. As long as you can apply what we've learned in the class to whatever subject that you are looking for, almost anything is fair game, right? So, you can almost think of the final project as your chance to kind of give a small lesson on a particular specialized topic in biomechanics for the rest of the class, okay? So, this class is kind of in an interesting position within our curriculum because we don't have a formal bioengineering department. This class and a couple others are probably as close as you can get. But in reality, there's so many really interesting and, specialized areas in biomechanics that you can, that are out there. We just don't really have time to cover all of it in the class. And so for the final project in this class, I want you guys to do do your own research, look into academic papers, and research on a particular topic, and apply everything that we've learned in the class towards that topic to do some analysis, okay? And so the main thing is that, you should think of it as kind of like a teaching opportunity where, you're researching, you and your group are going to be doing all the research into this topic, and you're going to get the chance to teach it to the rest of the class in terms of, what's important in this topic, what's kind of the modern, challenges with this topic, and, apply everything that we've learned, okay? So, there's two components to the final project. There is a final presentation that you're going to be giving during the last week of the semester. And then there's a final report that you have to turn in as well. So the final presentation, you can almost think of it as, you're giving a lesson in this. So it's kind of your chance to kind of stand up here at the podium and kind of give your lesson, while I sit in the audience, not relax because I have to be grading you, but, I have to, I get to listen to you guys for once. Okay. So actually, I have all the project requirements here, but let me actually go down to the list of topics first, because I think that's probably kind of a better place to start. So I have a list down here of some topics that people have done in the past, or topics that, I think would be interesting within the field of biomechanics, but, you can choose, so you can choose one of these topics, but of course you're free to come up with your own topic, as well, okay? No matter what, you and your group are going to have to email me and tell me what topic that you want to talk about anyway. And so if it's something from this list, I'll go ahead and approve it and reserve it for you guys. But if it's something that's not on this list, you can run it by me and we can talk about it as well. Okay. Okay. So here's just some sample topics that people have done in the past. And so one is, kind of a broad topic of sports performance. So this is kind of a, at least for me, I'm a big fan of sports. And so I think of sports a lot when I'm teaching this class. And so, you can apply, the idea is to apply what we've learned in the class in terms of, calculating muscle forces, calculating, you'll see in a second, doing like muscle force optimization, dynamic analysis, inverse dynamics, right? Applying that to a particular sport, to analyze, what's the most optimal way to do certain actions in that sport, okay? So for instance, last year, I had a group that did basketball. And so they did a biomechanical analysis of Steph Curry shooting a three-pointer. And so, they took Steph Curry's dimensions, the length of his arms, and, they looked at videos in terms of, the exact angle in which he kind of releases the ball, and talk about how that is an optimal from a biomechanics perspective in terms of, making a high percentage of three-point shots, okay? And so you can apply that to lots of other sports. I've had people do soccer in the past. I've had people do combat sports in the past. I've had people do tennis. So there's a lot of possibilities here. And so in parentheses here, you can see I said we can have multiple groups just because there's multiple sports. And so you can choose a sport of your interest. Okay. All right, another interesting one that I've had people do in the past is animal locomotion. And so even though we've been mostly focusing on humans, a lot of what we're learning in terms of, static analysis, dynamic analysis, you can apply that to animals as well. And animals actually provide a really interesting topic for biomechanics, as, animals have very different needs in terms of, how they need to get around, how quickly they need to get around, how quiet they need to be, different requirements for balance. Some animals live in very rocky terrains, and so that has to factor into, how their bodies are shaped as well. And so you can apply what we've learned to analyze, how animals, move. And so I've had people in the past do like jaguars or like cheetahs, in terms of, animals that run really, really quickly. And so in terms of how their bodies are designed, and how that can factor into their, their biomechanics. Have people done birds before? So if you're interested in applying what we've learned to animals, this is a great chance to do that. And again, multiple groups can do this just because, there's lots of different animal groups out there. And so, there's lots of really interesting things you can do with that. Number 3, surgical reconstruction. And so this is an area, we didn't really talk about too much in this class, but, for a lot of times when you have some kind of catastrophic injury to your bones or ligaments or tendons, you need to do some kind of reconstructive surgery to repair that. So a very popular one that occurs, or not, it's popular just because it happens often. Not to say that people do it just because they want to, but people tear the ligaments in their knees a lot. So my dad, had to have his ACL basically reconstructed because he tore it playing basketball. So this is an area that's, that has a lot of interest. And so, from this, for this project here, I'm interested to see, how, if you were to get your ligament kind of reconstructed, how would the properties of that differ from a regular one, and how would that affect kind of the biomechanics of your daily life? Okay. Number 4, prosthetic design. So this is kind of always an area of interest, and so I have a group that works on this almost every year. So how prosthetics are designed and manufactured with kind of the biomechanics of the human body taken into account. Okay. Equipment design. So I mentioned sports equipment here, but just any kind of movement equipment, how that is designed relative to the biomechanics of the body. That's kind of another really interesting one. Weightlifting exercises. So I've had groups in the past do powerlifting, deadlifts, shoulder raises, all that stuff. And so, how that factors in. This one's very natural. In fact, a lot of the examples that we've gone over in this class have been weightlifting exercises. And so, kind of diving more into that would be kind of interesting. Doing kind of multi-segment analysis would be really interesting for this as well. Robotics, locomotion, design, control, another kind of a very broad topic. But there's a lot of interest nowadays in designing robotics to kind of take over human tasks. And so how would you design something like that to kind of mimic what a human would do, or maybe there's a better way to do it. There's that as well. Okay. So basically the idea is that your group, and of course these are not the only ones, like I mentioned before. Your group would think about kind of what topic that you want to research, and and let me know. Just so that I can reserve you. So, the only limitation that I have is that, I don't want 2 groups working on the exact same thing. I want to have some variety in terms of what people are researching. But, thinking of a topic and agreeing on one from your group is kind of the first kind of thing that you have to decide as a group. Okay. Any questions on the potential topics? Okay. Okay, so now that we have the topics, let's talk about the specific requirements for the project itself. Okay. Okay. So ultimately at the end of this, you're going to be putting together a scientific report on your topic, and so the requirements of the presentation of the report, they're all going to kind of fit within that scope there. Okay. Okay, so the first aspect of the project requirements is some kind of research and some kind of explanation on the introduction and background information and the significance. Okay, so talking about why this topic is important, why it's an area of research, and so all of these topics, I'm requiring that you find primary literature for them. So if there's going to be scientific papers written about these topics, there's some there's obviously the reason why people are studying them. And so going over that here and kind of expressing that and explaining that is a big part of this project. Okay. All right, the next part is probably the biggest part. It's probably the part you're going to spend the most time on besides the research, which is the biomechanical analysis. Okay, so throughout this semester, we've learned lots of different techniques for how to analyze different biomechanical simulations or situations. So we've done a lot of static analysis. We've done a lot of we're working on the dynamic analysis now. So your goal with the project is to apply what we've learned to your situation. Okay. So doing static analysis of someone doing a deadlift, or doing a dynamic analysis of someone shooting a 3-point shot, right? That's going to be the that's going to be the big thing for your group to do. Okay. So feel free to make some assumptions and simplify the geometries, just because, in reality, a lot of these situations are going to be very complicated with very complicated, geometries and muscle forces and all that stuff. So you'll probably have to make some assumptions. So, don't be afraid to do that, and don't be afraid to ask for help if you're having trouble with this. Okay. In total, your entire report should have at least 5 of these analyses, and your final presentation should have at least 2 of them. Okay. And you can choose what type of analysis that you want as well. So I'm not requiring that you have 3 static analyses and 1 dynamic analysis and 1 optimization analysis. And so because every situation, every different topic is going to be very different in terms of what's going to be relevant for that topic. And so I don't want to place any limitations on you. If you're doing just static situations or static analyses, that's fine with me. You know, as long as they're all kind of sufficiently different. The idea with the biomechanical analyses, you know, if you think about this project in terms of like a lab report, you know, your biomechanical analysis is kind of taking the place of, you know, the data collection that you would normally do for an experiment. So the analysis is kind of, you know, how you're going to obtain your data, how you're going to obtain your numbers, and then you do some discussion based on the results of your calculations. Okay, and the discussion section is next. And so after you perform your analysis, you obtain your calculation. The next step is to discuss it. And so, you know, discuss why these numbers are relevant. And so why is, you know, when you compute this muscle force, why you compute it to be this, you know, why that's relevant to your project. And so, you know, let's say you're doing a, you know, an animal locomotion study, you know, you compute the muscle force in this animal's legs to be this. You know, why is that significant? So, you know, why does that make this efficient for that animal? You know, is this a lot more force than a human can output? You know, is this something that an animal requires? You know, basically answer questions of, you know, whenever you get some data, you know, ask yourself, why is this kind of relevant? Why is this kind of important? And that's what you're going to discuss in the discussion section. Okay. You'll see that there is a template for the report. And so, you know, that template will kind of give you some ideas in terms of, you know, some discussion questions that you can answer. Okay. Okay, sources. And so, you know, those three sections are there. Those are the three main sections of your report. But of course, you know, a big part of this project is you know, researching primary sources. And so, altogether, your group needs to have at least 12 different sources. 4 of these sources need to be from some scientific journal. So that means that's primary literature. Okay. So if you don't know how to look for primary literature, usually I like to use Google Scholar. And so you go to scholar.google.com and you search your topic, and then you try to find some that gives you some information. Okay. The good thing about primary literature is that oftentimes their primary literature will be, you know, some kind of scientific publication where they ran some experiments or maybe they ran some simulations. And so you can use a lot of their results, or you can use a lot of their data for your analysis yourself. And in fact, you know, a big part of this project is, you know, you need to be able to find the data yourself in terms of, you know, how long your limb should be, you know, for a particular athlete, a particular animal. How much weight do you need to apply? You know, how much force can the muscles apply? And so a lot of that information is going to come from your primary research. Okay. All right. Any questions so far before we talk about the deliverables for the project? Okay. Okay, so deliverables. So there are 2 main deliverables for this project. So one is a final presentation. So, you know, like I mentioned before, the final presentation is something that your group is going to be giving on the final week of the semester. So half the groups are going to go on Monday. The other half are going to go on Wednesday. So this is the final week of lectures, by the way. This is not finals week, and so you know, you're going to give the presentations during our normal lecture times. So you can think of the presentations, you know, as a brief summary of the contents of your report, and it should be structured as if, you know, you were giving a lesson to the class. Okay. The presentation is going to be roughly about 15 minutes long. I think, you know, we don't have that many students in the class this semester, so I think they can tend to be on a little bit on the longer side. So they may be 15 to 17 minutes. But, you know, I do expect everyone to participate in the presentation as well. Okay. So, you know, of course, the final week of the semester, that's, you know, I know there's a lot of other stuff going on. So I don't expect your projects to be completely done at that point. So it's not that your final report has to be written, but you should have enough done at that point in terms of the research, like all the research into the literature should be done. You should have done, you know, a few of the biomechanical analyses. And so, you know, you should have enough to present by that time. Okay. And then the other deliverable for the project is the final report. So the final report is the final deliverable, and everything should be in the final report. Okay. All of your literature review, all of your introduction, all of your analyses, and it should all be formatted really well as well. Okay. So the due date for the final project, this is a typo. It's not a Monday, it's actually gonna be a Sunday. It's gonna be Sunday, December 22nd. Okay. So that's the Sunday after finals week. Normally I have the projects due on the Monday after finals week, but, you know, because the semester goes so late this time, the 23rd is really short because, you know, I want to grade all of them before Christmas. So Sunday is kind of the latest that I can push it in, and I can't really go anything beyond that. So Sunday, December 22nd, that's going to be the final due date. Okay, and you only need to submit one report for the whole group. Okay. All right, so the final report components, you know, I have a template posted for the final report. In terms of length, just because people ask me every year, I don't have a length requirement. You know, I'm not going to mark you up or mark you down based on the number of pages that you have. You know, I'm strictly grading just based on the content of your report, making sure that all of the required sections are there, everything is explained in detail, all your analysis is done correctly, the numbers make sense. But if you want a rough average in terms of where most reports end up, they end up kind of in the range of about 18 to 25 pages, and that includes the figures. Okay. And in fact, you should include figures. And so, you know, there should be free body diagrams. There should be, you know, images that kind of enhance your report as well. Okay. I've had reports that have gone way over this. I've had, you know, people turn in 60-page reports that I've marked poorly just because it was all fluff. But I've also had pretty short reports that are very efficient, you know, maybe 12, 13, 14 pages, you know, that get everything done. And so, you know, and I give those very good grades as well. So, you know, it's, you know, writing more pages doesn't mean that you are going to get a better grade. In fact, you know, it kind of annoys me because it makes me, you know, have to scroll more and read more. And so, you know, go for quality, not for quantity, for sure. But most reports on average just over the years have been around 18 to 25 pages. And so, you know, that's just kind of the average. And here's all the sections of the report, you know, which we've kind of talked about. Okay. Teams. And so, you know, I've mentioned this, you know, throughout today, but, you know, this is a group project. So it's not something you're going to do on your own. So, you know, the group sizes will be about 4 students. We may have a couple groups that have less than that, just because I think we have about 29 students in the class. So I'm anticipating that we're going to have about 8 groups. And so, you know, so most groups will have 4 students, and then some groups will have 3. Okay. And it splits up really nicely too. So during the final week, we'll have 4 groups go on Monday and 4 groups give their presentation on Wednesday. Okay, so you guys can choose your own groups. You know, I'm not going to choose. You guys are adults. I'm not going to choose your groups for you. But as soon as you guys form a group and as soon as you guys come up with a topic, you know, make sure to email me because the topics are kind of first come, first served. And so usually it doesn't. There's enough variety in terms of the topics in this class that 2 groups usually don't think of the same thing. But, you know, always better to kind of, you know, email me and get it settled first. Just so that you can start doing your literature review and stuff like that. Okay. If you're having trouble finding a group, you know, let me know as well. And so, you know, there's always a, you know, kind of a group of you know, of people that, you know, that I kind of have to force them together just because of, you know, you know, there's, we can only have about 8 groups. So if you're having trouble finding a group, just let me know. And I'll put you guys together, you know, as quickly as I can. Or maybe if you have a pair, so let's say that you have a buddy and you're looking for one other person to round out your group, just let me know too, and I can probably find someone to fill in that spot. Okay. All right. Any questions on the project at all? So from the teams to the topics or just the requirements or anything. Okay. Graduate project. So I don't have it here, but there are a couple of you that are taking this for grad credit. So for the grad assignment, you know, your assignment will be to do an additional literature review. And so as part of your group, you know, you have to research 12 different sources and 4 primary literature. If you're a grad student, I want you to do 1 additional primary source, you know, look up 1 additional paper. And then I want you to do write a summary of that paper for me. Okay. So this is a very common task if you do you know, any kind of academic research, is to do kind of a literature review and write a summary. So that's basically what I want you guys to do. Okay. Since you're going to be looking into the primary literature anyway, you know, just look up 1 extra paper. That extra paper can have something to do with your project, or it can be on another topic if you want to. The only requirement that I have is that it has to be, you know, within the realm of biomechanics. If you want me to look at the paper, so let's say that you research something and you want me to take a look at it, you can send it my way and I can tell you whether it's good or not. Okay. All right, so that's the final project. So, you know, definitely, get out there and form your groups, and then, you know, just so that you can start researching your topic. Okay, because the end of the semester will be on us kind of sooner rather than later, because we have the midterm exam that's coming up in a couple of weeks. And then, and then right after that, we have 1 week after Thanksgiving and then presentations after that. So yeah, it's the end of the semester is going to go pretty fast for us. Okay. All right. So let me go ahead and bring it back to the iPad here. Okay. All right, and so for the rest of class today, let's finish up our lecture notes on human motion kinematics. Actually, that reminds me, I think one of the most creative analyses that I saw in the final project happened a couple years ago is that, I had a group that did their report on the biomechanics of rowing. And so, I don't remember if they downloaded a special software for this, but basically they had set up a camera in a guy's room. And then he had a rowing machine there, and then he basically rowed. And they basically did a human motion analysis on it. So they placed kind of virtual markers on the person's elbows and the wrists and their shoulders, and they track kind of their motion throughout the entire rowing motion. And they were able to compute things like muscle forces and joint reaction forces all through the motion. It was really cool. And so that's definitely something that you can consider as well. Okay. All right, human motion kinematics. And so where we last left off, we were talking about the idea of using transformation matrices. Okay. Okay. So just to kind of, refresh your memory, human motion kinematics, when it's analyzed in kind of in most modern settings, uses optical motion capture. Okay. So basically the idea is to attach these motion tracking markers onto the outside of a person's body. And then as the person goes through the motion, the positions of those trackers can be tracked using a computer and camera. Okay. And so from there, in order to get that data and put it in a form that we can use for analysis, we have to form the transformation matrices, okay? So these are used to compute transformation matrices basically for each body segment of the person's body. Okay. And remember, there's two reference systems that we have to keep track of for each body segment. Okay. There is the anatomical reference frame. Okay. And so that is the ARF. Okay. And so what's special about the anatomic reference frame is that this is usually aligned with the person's body segment, right? And so, every body segment usually has some kind of underlying bone or some kind of underlying axis. And so the anatomical reference frame is aligned to that body segment. Okay. The problem with the anatomical reference frames is that in order to basically define the reference frame itself, we have to put the motion tracking markers on a kind of an inconvenient location, which usually kind of gets obscured from the cameras quite a bit. And so in addition to the anatomical reference frame, we also have what's called the tracking reference frame. Okay. And so we call that the TRF. And so the tracking reference frame usually, usually you're going to place the markers on on a part of the body segment that's easily tracked by the cameras. Okay. But the problem with the TRF is that, it's because the markers are placed in convenient locations, you can't really use them to compute joint angles because they're not really aligned with the body segment that it's attached to. Okay. And so for every body segment that you want to track, there's usually going to be two sets of markers on that body segment. One that's going to be for the ARF and one for the TRF. Okay. Sometimes, you may have a marker that's used for both. Maybe it's one that's aligned with the body segment, but also in an easy to track location. But generally, for most body segments, you're going to have two sets of markers on there. Okay. Okay. So for any given body segment, let me go ahead and draw kind of the usual one that we have here, which is the arm. Okay. You may have, two markers here. Okay. And we're just going in 2D here. So let's say, markers 1 and 2, that's going to be used to establish the ARF. So you notice how 1 and 2 kind of, one's on kind of the one end of the segment, the other's on the other end. And so if you were to draw kind of a line in between the two, right, you can kind of imagine that line that I drew right there kind of aligns with the bone that's underneath. Okay. And so for the upper arm, that would be your humerus, right? So that arm would be that line would align with the humerus. And if we define this to be, maybe the x-axis of that anatomical reference frame, you would have the x-axis aligned directly with that humerus. Okay. And then you can draw like a y-axis that goes this way perpendicular, right? And then off we go. On the other hand, those two trackers may not be easily tracked. And so, maybe let me use a color that's different. Okay. Maybe we put two other markers right here. Okay. 3 and 4, and we'll put those right kind of on the outer side of the arm themselves. Okay. And so markers 3 and 4, right? These establish the TRF. Okay. Just because they're in positions that could be, easily tracked by the cameras. They're always kind of on the outside surface of the body. They're not going to be, covered by the torso or anything like that. Just like that. Okay. So I think where we left off last time is, how are we supposed to relate these two things, right? So the way that we relate them is to compute their transformation matrices. Okay. And so for both of these, coordinate systems here, we're going to compute a transformation matrix. Okay. And so this transformation matrix is going to be between the ARF and another reference frame, which we call the lab reference frame. Okay. And I'll explain what the lab reference frame is in a second. Okay. And then same thing for the TRF. For the TRF, we're going to define a transformation matrix that's between the lab reference frame and the TRF. Okay. So lab R ARF and lab R TRF These are transformation matrices between the lab reference frame and the local reference frames attached to that body segment. Okay. So what is that lab reference frame? Well, the reason we call it the lab reference frame is that, traditionally these motion capture studies are done in some kind of biomechanics laboratory, right? And so the laboratory itself, we consider to be kind of fixed in space. And so the lab reference frame is nothing more than just some kind of fixed reference frame. And so what we can say that this is some fixed reference frame that we just attach to Earth. Okay. The point is that it's not moving. And so we have some origin that's in the room, might be in maybe like the corner of the room over there or something like that. We just need to have some kind of, place to define the reference frames from. Okay. Okay. And that lab reference frame is actually going to be really important because, you'll see that when we do a problem here, that, that lab reference frame is actually going to be used to establish, both of the coordinate systems. Okay. Okay. So actually, let me actually talk about that right now. Okay. So usually when you have these motion capture studies, the first things that you're going to compute are going to be these two things. Okay. So you're going to compute the transformation matrix between the lab reference frame and the ARF and the lab reference frame and the TRF. Okay. So to compute these reference frames or compute these transformation matrices, one way that you can do it, or probably the easiest way that you can do it, is to compute the coordinate systems or the coordinate axes, X and Y axis. We're going to start with 2D of each of the local reference frames with respect to the lab reference frames. Okay. So you'll see in the next example that, if you're looking at the motion capture markers for a particular body part, you'll have, the XYZ locations, or in our case, just XY locations of each of the markers on that person's body. And so what you can do is you can use those positions to compute the local X and local Y normalized, and that's going to be your transformation matrix. Okay. All right, any questions on that before we jump into an example? Okay. All right, so let's look at an example. Okay. So let's look at the motion capture analysis of a person's hand. And just to keep things simple, we're going to do it in 2D. Okay. Okay. So let's do this. Should have just traced my own hand. That's the ugliest hand I've ever seen. Okay. Okay, I got the right number of fingers right. That's a good start. Okay. So we have we're gonna have 4 markers on here. Okay. And we're gonna know the X and Y positions of both markers, of all the markers. Okay? So let's say marker 1 is right here. Marker 2 will be right at the wrist. Marker 4. And we'll say marker 3 is near the pinky. Okay. Okay, let me give you the positions of all 3 of the markers. So let's say marker 1, its position relative to the lab origin is 97.81 centimeters. That's its X coordinate, and its Y coordinate is 7.42 centimeters. Okay. Marker 2, its position is 102.11 centimeters. And its Y position is 4.21 centimeters. Okay. Marker 3, its X position is 105.27 centimeters. And its Y position is 11.46 centimeters. Okay. And then marker 4, its X position is 99.14 centimeters. And its Y position is 17.09 centimeters. Okay. Yeah.
Will we always assume marker 1 and 2 are paired and 3 and 4 are paired?
Not necessarily. The numbering is kind of arbitrary.
Okay.
Yeah. Okay. And so on this hand, we need to establish both the anatomical reference frame and the tracking reference frame. Okay. So that's going to be part A and B of the problem, is to compute. We're going to compute the transformation matrices between the lab frame and ARF. Okay. Between the lab frame and ARF, and the lab frame and the TRF. Okay. Okay. And so of course we need to pair these. And so, 2 of these are going to be used to establish the ARF, and then the other 2 are going to be used to establish the TRF. Okay. Okay. So for this one, let's say, and so you can kind of tell just based on where the markers are placed. And so generally your ARF, or your anatomical reference frames, they're going to be positioned in a way where one of the axes is going to go kind of as far down the length, or kind of be as parallel to the long axis of the body segment as much as possible. Okay. So for the hand, the primary motion of the hand, can kind of be tracked, if you put one marker right on your wrist and another marker on the tips of your fingers, right? So we don't have a marker on the middle finger here, but we do have a marker on the pointer. Okay. And so actually, if you connect markers 2 and 4, that's going to be your anatomical reference frame. Okay. So markers 2 and 4, we're going to use these to establish the ARF. Okay. But maybe, maybe just kind of based on the position of the hand, maybe the marker 2 has to be placed on the bottom of the wrist. Okay. Just so that you kind of get the whole kind of, it's not just the top of the wrist. It's you're trying to align the ARF with the bones as much as possible. Okay. So in order to track this, we have to establish markers 1 and 3. Okay. And so markers 1 and 3, you know, maybe these are placed on the top of the hand. These are kind of really easy to track throughout the motion. So markers 1 and 3 are going to establish the TRF. By the way, for the problems that you guys are going to be doing, you know, I'm not going to have you guys guess which marker is going to establish a TRF and ARF. I'll tell you, but I'm just, you know, I'm just kind of giving you some trivia in terms of the logic, in terms of how these are usually defined. Okay. Okay. So let's start with the ARF, just because I have it first there. Okay. So let's compute lab R ARF. Right. Knowing the fact that markers 2 and marker 4, these are going to be used to establish the ARF. Okay. Okay, so first of all, you know, we're in 2D, and so we only need an XY, you know, XY coordinate system. Okay. So usually the way that these work is that, you know, when you're given two markers in 2D, right, the connection or the line in between those two markers are going to establish the x-axis for your reference frame. Okay? So let's draw a line between markers 2 and 4. Okay. And we're going to define this as the x-axis of our new reference frame. Okay. So we can do that because we have the positions for all these points right here. Okay. Okay. So we want the line to go from 2 to 4. Okay. And so we're basically going to make the assumption that this marker 2 is going to be the origin of our system. Okay. And so you want the vector to go from marker 2 to marker 4. Okay. Again, usually the problem is going to tell you which of your markers are going to be the origin. But you know, the logic for this one is that, you know, the origin is the one that's more proximal to the center of the body. Okay. And so because the wrist is more proximal than your fingers to the center of your body, you know, it makes sense to have the wrist be the origin of your anatomical reference frame. Okay. Okay. So we need a vector that goes from marker 2 to marker 4. Okay. All right. So to define a vector that goes between 2 points where you know the coordinates of those 2 points is to take the coordinates of the endpoint and subtract the coordinates of the starting point. Okay. And so since our ending point here is 4, let's take the coordinates of point 4. So marker 4 has an x coordinate of 99.14 centimeters. Okay. And let's subtract the x coordinate from point 2. Okay. And so the x coordinate for marker 2 is 102.11. Okay. So that's the x component of that vector. And then the y component of the vector will be the same things, but for the y components. And so the y component for marker 4 is 17.09 centimeters. Okay. And then the y component for marker 2 is 4.21 centimeters. Okay. So we perform this subtraction, which brilliant me, I only printed out the question here. I didn't actually print out the solutions. So I just pull up a calculator on my phone real quick. Okay, so we have 99.14 minus 102.11. That is a minus 2.97 centimeters. Okay. And then for the y component, we have 17.09 minus 4.21. So that is 12.88 centimeters. All right, and so that's our x-axis. Okay, so our x-axis has coordinates of minus 2.97, comma 12.88. Okay, but we're not done yet, and so we can't just leave it like this. So we want to normalize this normally. Okay? And so to normalize a vector, all that really means is to make sure that it has length 1. Right? So the exact ratio between the x and y components stays the same, but we divide the entire vector by its magnitude to make sure that it has magnitude 1. Okay? Okay. So let's go ahead and do that. And so we're going to divide by the magnitude. Okay. And so first, let's compute the magnitude of the vector. So the magnitude is going to be square root of each component squared. So we have square root of 2.97 squared plus 12.88 squared. Okay. So let me just punch that into a calculator really quick. Okay, so the magnitude of our vector here is 13.218. Okay. And so let's divide both components by that. Okay. And so we divide both components. We have negative 2.97 divided by 13.218. And so that's going to be a negative 0.225. We'll just keep it consistent. We'll just go 3 decimal places. Okay. And then we have 12.88 divided by 13.218. And so that is at 0.974. Okay. So let me just go ahead and box this for a second. We're not done just yet, but this is the this is a good pausing point. Okay? So this is the x-axis of our ARF. Okay? Defined relative to the lab reference frame. Okay? Because remember, the coordinates that we use to compute these, the coordinates of marker 2 and marker 4, those were defined relative to some origin that exists somewhere in that group. Okay. And so that origin is what defines our lab reference frame. Okay. All right. Any questions on this? Yeah.
Would we still call it B24, or would we give it a different name now that it's normalized?
Oh, yeah. So we can call it V24 hat. Yeah. Yeah, we're going to put this in the transformation matrix really soon. Yeah. Okay, so that's the x-axis. So that's one part of our transformation matrix. The other part is our y-axis. Okay. Okay. And so, like I mentioned before, so to get the transformation matrix between the ARF and the lab reference frame, you need the x and y coordinate axes defined relative to the lab reference frame. Okay, so we have the x-axis, we have one of them. Now we need the y-axis. Okay? So what do we know about the x and y axis traditionally? So, this is kind of irrespective of whether it's a local reference frame or the fixed one. The y-axis always has to be perpendicular to the x-axis. Okay. That's always a requirement. So all of the coordinate axes of your reference frame have to be perpendicular to each other. Okay. But to be perpendicular to a vector, there's technically infinite possibilities to this. So if you're looking at three-dimensional space, right? And so if I were to have a vector like this, technically this vector is perpendicular to it. This vector is perpendicular. This vector is perpendicular. So, you have kind of an infinite amount of vectors that are perpendicular. So we have to kind of constrain this a bit more. Okay. And so our y-axis has to be perpendicular to the x-axis, but it also has to be within the plane of the page. Okay. Okay. So, we're kind of making the assumption here that the z-axis is kind of pointing out of the page. Okay. Okay. And so actually, even with just two markers here, we have everything that we need to define the y-axis. Okay. I think I might have misspoke, I think sometime last week where I said, you need three markers to define a coordinate system in 2D. Actually, in 2D, you only need two markers. You need a third tracker for 3D motion because you need that extra marker to define your extra axis. But in 2D, just two markers is enough. Okay. All right, so the way we're going to do this, so the way to basically make sure that our y-axis here is perpendicular to our x-axis and stays within the plane, we're going to take a cross product. Okay. And so we're going to take the cross product of two different vectors. And so, what do we know about vector cross products? When you take the cross product between two vectors, you get a third vector, and that third vector is perpendicular to both of the input vectors. Okay. And so it makes sense that, when we take our cross product here, we're going to take the cross product of the vector that we've already determined here. Okay. So we're going to take the cross product of minus 0.225, comma, 0.974. Okay. And we're going to take the cross product with that with another vector. Okay. So we're going to do something a little bit strange here. So even though this is a 2D example here, in order to properly take the cross product, we actually need to do it in 3D. Okay. And so I'm going to add a z dimension here. Okay. And so I'm going to assume that the z component of this vector is 0. Okay. So this right here is our x-axis that we've already defined. Okay. And I'm going to take a cross product with this with a vector that's pointing out of the page. And so a vector that's pointing out of the page, that's just a simple unit vector in the z direction. These have 0, 0, 1. Okay. So let's go ahead and take the cross product between these two vectors. So usually what I like to do for cross products is I like to set up this kind of imaginary 3x3 matrix. And we're going to take the determinant of that matrix. Okay. So the first row of the matrix are going to be the ijk vectors, which are the unit vectors in the x, y, and z direction. And the next two rows are going to be the two vectors that we're taking the cross products of. And so second row is going to be minus 0.225, 0.974, and 0. And then our last row is going to be 0, 0, 1. Okay. Okay. So let's go ahead and take the determinant of this matrix. Just because of the interest of time, I'm going to not software update. Go away, Apple. I'm just going to kind of do the first step of this calculation here, and then I'll leave you guys kind of do the details for it from there. Because I do want to mention about how we actually compute joint angles from this, which is kind of the whole point of going through this whole exercise, right? Okay. So the next step of this calculation here is we're going to take the I component of this determinant, and so I'm going to cover up the first row and the first column, and so we end up with 0.974, 001 I. Okay, minus determinant of the middle. So I'm crossing out the first row and the second column. So that's a minus 0.225001 J plus determinant of the last set, this minus 0.225, 0.97400 K. Okay. Actually, this is pretty easy. Let's just go ahead and do this. Okay. And so what we get from this is, for the I component, we get 0.974 I plus, so we have two minuses that are going to cancel out here, 0.225 J. And then our K component is 0 because, we want it to be in the plane. So that's good. Okay. And so our y-axis, it ends up being 0.974, comma 0.225 positive. Okay. So finally, we can write out our transformation matrix. So our transformation matrix, this was ARF. Okay. So in 2D, we have a 2x2 transformation matrix. Okay. And so the way you're going to form this is that the first column of your transformation matrix is going to be the x-axis of your ARF. The second column is going to be the y-axis. Okay. So we're just going to write the components of our x and y axes into the columns of the transformation matrix. Okay. So for the x-axis was a minus 0.225 and then a positive 0.974. And then for the y-axis, we have 0.974. By the way, we know this one is normalized already. And then 0.225 positive. Okay. All right, and so that's the transformation matrix of your ARF right there. Okay. So to do these problems, you need to establish the origin, which marker is establishing the origin. Establish one of your coordinate axes. Usually it's going to be your x-axis, and then you're usually going to do a cross product from there to determine the other one. Okay. All right, any questions on this? Okay. All right. So, that's not the whole problem there. So, the other part of the problem is to find the TRF as well. But finding the TRF is basically just a repeat of this as well, just using a different set of markers. Okay, so it's a little bit repetitive, so I'll leave that to you guys. Okay. Okay. So now, let's kind of finish this up. So the last thing I want to go over today is to talk about, how can we actually compute the joint angles of these using these transformation matrices. Okay. Okay. So, if you recall from the end of class on Wednesday, right? I think for the 2D transformation matrix is kind of the easiest to determine. Um, when you have two coordinate systems that are next to each other, right? The transformation matrix here tells you, how one coordinate system is measured relative to the other. Okay. Excuse me. And so in particular, if you look at the transformation matrix that we just computed, right? That is that shows the relative orientation of the ARF relative to the lab reference frame. Okay. And so in particular, if you take that result, and so let's take the minus 0.225, 0.974, 0.974, 0.225, okay? And so if we relate this to our formula for our 2D transformation matrix, right? This is cosine theta, sine theta, minus sine theta, and cosine theta, okay? And so based on this, you can compute the angle, right? And so these two coordinate systems are going to look like the following, right? So maybe we have an XY coordinate system. This may be the lab frame. Okay. And then, angled from that, we have the ARF. Okay. And so based on that result and based on what we compute here, we can compute that angle. Okay. It may seem a little bit disorienting because, we have both negative 2.25 and positive 2.25 equal to cosine theta. But, that's just kind of a consequence of some of the transformations that we do. Same thing with, minus sine theta is equal to this, and then positive sine theta is equal to that. So usually in these situations, I just take the positive results, okay? Because I know this will give me an angle that's in the first quadrant, okay? And same thing here. So I would take, positive sine theta is equal to 0.974. And so those both should give you that same angle. Okay. Okay. So that part's really easy. That part is, just relating kind of entries in a matrix. You relate it to, the formula, and you use the formula to compute the angle. Okay. But ultimately what we want is we want to be able to compute the angles between two successive, body segments throughout a motion capture cell. Okay. So to compute the joint angles between two body segments, okay, what you want to compute is you want to compute the transformation matrix between the ARF of body segment 1 and the ARF of body segment 2. Okay. Remember, we can't compute joint angles from the TRS. We need the ARS to compute the joint angles. Okay, and not only do we need one ARF, we need two ARFs. Okay, so an ARF from one body segment and the ARF from the body segment that's next. Okay, so for example, if we look at the previous example where we computed the ARF of the hand basically, right? If we wanted to compute the joint angle of the wrist, we need both the ARF of the hand and the ARF of the what's it called, the lower arm. My mind just blanked. Okay. Okay. And so in other words, we need R ARF can, and ARF arm. Okay. Okay. So how do we obtain this? Well, we can take advantage of some of the properties of the transformation matrices themselves, right? Remember, there's two main properties of transformation matrices. On the one hand, there is the transpose property, where if you transpose a transformation matrix, you kind of swap the direction of the transformation. Okay. And so we'd have 1R2. If we transpose that, that's equal to 2R1. Okay. So you swap the direction. The other property of the transformation matrices is the transitive property. Okay. And so we talked about this kind of at the end of class last time when we were talking about, the different orientations of the airplane, where if you multiply two transformation matrices next to each other and they have kind of a common thread between them, you can kind of cancel that out in the middle. Okay. So for instance, if you have 1R2 and you multiply that by 2R3, okay. The 2's here are going to cancel out and we get 1R3. Okay. Okay. So we can use these two things to obtain the result that we need above. Okay. Because, for any given motion capture study, we can do basically the exact same thing we did in the example, but for two successive body segments. Okay. So let's say that we compute lab R ARF, and I'm just going to say ARF1. Okay. So that's going to be the ARF of one body segment. And we can do the exact same thing and compute the same lab R ARF2. Okay. So what we can do, right? If we take the transpose property, so let's transpose this. Okay. So if we transpose this, we get lab R ARF1 transpose. That's going to swap the positions of our two systems here. So we have ARF1 R lab. Okay. And if we multiply this by lab R ARF2, okay, we can cancel this out, cancel out the lab, and we obtain the result that we want. Okay. So it's all good, right? But where does the TRF come into play, right? We're talking all about this ARF, but we haven't factored in the TRF yet at all. Okay. So I've kind of led you guys on a little bit here, right? So the calculation isn't actually this simple here, because what's the problem here? Okay. Remember, the problem with ARFs in general with motion capture is that they aren't often seen throughout the motion. Okay. So, you may be able to compute this, this transformation matrix at one point, maybe during calibration. But generally speaking, this transformation matrix is not going to be available throughout the motion. Okay. So this calculation, you may be able to do it in one static scenario where all the cameras kind of line up with your ARFs, but generally speaking, that's not going to be possible. Okay. And so the reality is actually a little bit more complicated. Man, I need like 5 more minutes, but okay. Let me just write it down real quick and then we'll go through it next time. So basically you have to take the TRFs into account. Okay. So you actually need to multiply 4 transformation matrices by each other. Okay. And so the way it works is like this. And so okay. So the first transformation matrix is going to be between the ARF of one body segment and the TRF of that same body segment. Usually you can obtain this through calibration. Because even though the markers on that body segment are going to be moving, relative to each other, the ARF and the TRF are not going to be moving relative to each other on the same body segment. Okay, so you can compute this at the beginning, and it's actually going to stay static. Okay. Next thing you want to do is you want to compute the transformation matrix between the TRF of segment 1 and the lab. Okay. And you're going to multiply that by the transformation matrix between the lab and the TRF of segment 2. Okay. And so since these are TRFs, these are tracked during the motion. And so these are going to change with time. Okay. And then the last transformation matrix is going to be the calibration matrix. And so that's going to be of segment 2. So that's TRF of segment 2 and the ARF of segment 2. So this also is in calibration. So it's static. Okay. And so if you multiply all those transformation matrices together, you're going to see that all of the inner arguments are going to cancel out. And what you're going to end up with in the end is a transformation matrix between ARF1 and ARF2. Okay. So it looks really complicated here, but this is typically how it's done. So you compute these 4 transformation matrices. 2 are static. The ones in the end are static because they're in calibration. And the 2 in the middle are what's going to be tracked during the motion. Okay. All right, any final questions on this? Okay, all right, so I apologize for going over a bit. I know I went about a few minutes over time. I'll kind of recap this at the beginning of lecture on Wednesday, and then we'll move on to the next section here, which is inverse dynamics. All right, so thank you guys for coming today. Definitely start thinking about the groups and what topics you want to do for the final project, and let me know as soon as you have a topic. All right, so thank you guys. Hope you guys have a good rest of your day, and I will see you on Wednesday.
I just wanted to ask you something related to like advisor.
Oh, sure.
So how do you as an advisor with my question?
Yeah.
Probably don't like
Yeah.
that.
Mhm.
You recommended like a course like advisory school is like a
Yeah, so that's been 4:30.
4:30.
Yeah. So that's you're gonna learn partial differential equations in that class. So whether you do grad school here or you do grad school somewhere else, you have to take a course like that because
Okay.
a lot of grad courses rely on.
Is that it's not a grad course, I can still take it.
You can still take it.
Okay.
Yeah, so you can take it as a tech elective. If it's your 5th technical elective, you can actually count it for grad credit here. But just the knowledge will be really useful if you're going for a master's.
All right, thank you.
Yep. Mhm.